Hello everyone, welcome to Trolling with Logic. It is 12th of May 2013, 6 PM in the UK and 1 PM Eastern Standard Time in the US. We are a regular show on issues of science, skepticism, secularism and philosophy. Just a quick note, you may call in at any time, just simply add the Skype contact Trolling with Logic. Please send us a little gist of what your question is and we will add you in time. Also, by calling in, you do grant us permission to use your likeness because the show is later uploaded to YouTube and iTunes for later viewing, so no funny business with the DMCAs. So I'll very quickly introduce my team today and welcoming back from his long sabbatical, Kitch.
Hey guys, great to be back.
And as always, we can welcome in Martimar.
Hi everyone.
And making another one of our special appearances, the always charming Wobble.
Hello!
Great to have you. So, I'll very quickly introduce our guest, well-known cosmologist and physicist, author of the books From Eternity to Here, if I got the title the right way around. Also, and I can't remember, the particle at the end of the universe. They've all got very long titles, so forgive me if I mispronounce it. And you may know him from the Histories, the Universe series, which I'm a huge fan of. And there was also the series with Morgan Freeman. The name escapes me right now. But please, everyone, welcome Sean Carroll to the show.
Hello.
Welcome.
Sean? Hello, Sean. I don't think Sean can hear us for some reason.
Now I can hear you. You're fading in and out, but just for the last few seconds you were. But before that, everything is fine. So
all right.
I'm going to assume everything's fine.
All right, that's great.
I didn't touch any of the tech. It's not me.
So I think we'll hand over to our physics guru on our show anyway, Martimar. You've got a lot of questions lined up.
Yeah, well, I don't know if I have a lot of questions, but they might lead to a lot of follow-up questions. Yeah. At least I hope so. Now, I understand you've been looking a lot at time. Well, there are plenty of different ideas about time and its role in cosmology. And so basically, what's your take on it?
Yeah, well, my take begins by saying that it's not that big of a mystery, actually. I think that people get a little goofy when they start talking about time, acting as if it is some absolutely inexplicable thing that we'll never figure out. I think that we kind of figured out what time is in and of itself. Newton had a pretty good idea of what time was. It's just that you have the universe full of stuff scattered throughout space, and that universe happens over and over again, and it's a slightly different configuration of stuff every time it happens. And time is just the label on the different moments of the universe. Time is like the page numbers in the book of the universe that takes you from the beginning to the end. It became a little bit more complicated with Einstein, because he said that time and space are tied up with each other in space-time. But that's not that big a deal. That just means that there's many different ways of slicing the universe into space versus time, but time is still there. The interesting aspects of time are not what is it, or what is its essence or anything like that, but why does the stuff in the universe behave one way if you trace its path toward the future, and very differently if you go into the past? That's the arrow of time. Why is the past different from the future? And even that wouldn't be very mysterious, except that all the laws of nature that we know about treat the past and future exactly the same. So there is a physics mystery why the past is different from the future, but what time is, how it works, that makes perfect sense. When someone says, the podcast is going to begin at 1300 hours Eastern time, you know what that means. No one is baffled. No one is scared by that kind of talk.
Okay, Martin?
Yeah. So when it comes to the whole idea of time beginning, I understand that there are different ideas among cosmologists. Stephen Hawking has this idea of the idea of before the universe is like north of the North Pole, and others say that perhaps inflation just marks a beginning of a certain period in time, but time itself is eternal, or something like that. Could you talk about that a little?
That's exactly right. I mean, this is just one of those questions where, if we're honest, we have to say we don't know the answer. There's lots of different possible answers that are on the table. The universe could have begun, literally, at what we call the Big Bang. It's possible that there is no moment of time earlier than the Big Bang. But it's also possible the Big Bang is just a phase the universe went through. And there was something before the Big Bang, some universe, some quantum mechanical state of the universe, maybe not even a classical space-time, but nevertheless some quantum reality. We just don't know. So we're right now in the business of writing down proposals and figuring out what might fit the data, because that's how science works.
Okay, we've already got some. Do you have a question, Martima? Because there's some chat room questions coming in.
No, I'm not looking in the chat room. So if someone has asked something relevant to what's been said so far, go ahead.
Okay, it's a question from one of the guest chatters. Sean has previously talked about the arrow of time. Now, does entropy define the arrow of time, or is entropy time itself?
Yeah, it's not right to say that entropy is time itself. Entropy, for those folks out there who haven't yet read my book, entropy is a way of measuring the disorderliness of something. So if you have cream and coffee separate, that's low entropy. If you mix them up all together, that's high entropy. And we all know that entropy tends to go up as time goes on. That's the second law of thermodynamics. So it is a profound and true and fascinating and puzzling statement that all of the differences that we can put our fingers on, all the sort of crucial deep down differences between the past and the future, can ultimately be traced to the fact that the entropy was lower in the past and is going up toward the future. So it is correct to say that the arrow of time is due to the increase of entropy in the universe. The universe started out very orderly, very organized, in a very special state, and it's growing increasingly chaotic and messy and disorderly. And that explains everything about the difference between the past and the future. It explains why you remember the past and not the future. It explains why you can make choices about the future but not make choices about the past, and so on. However, even if there were no entropy, even if there wasn't an arrow of time, there would still be time. There is, after all, no arrow of space. If you're out there in your spacesuit, all the directions of up, down, left, right, forward, backwards seem equally physically equivalent to each other. There is no intrinsic arrow of spatial direction, and yet space is real. So it's very, very important to distinguish between the arrow and space or time themselves. So entropy defines the arrow of time, but it's certainly not time.
Quick question here. I've been sort of looking into general relativity at I guess you could say a semi-technical level. The property you're talking about, is that what is meant by space-like and time-like dimensions?
Well, it's related to that, but it's not exactly quite the same thing. There is this interesting fact about the world. So Einstein and Minkowski and others understood that what we call space and time are both part of one big thing called space-time. But clearly they're different, right? I mean, you can take a left turn very easily. You cannot take a left turn into yesterday very easily. So there's something different about space and time. And that difference, the mathematical expression of that difference, is that the distance between 2 points is very different if those points are separated by time than if they're separated by space. So if they're in a time-like direction, if the distance between two events in the universe is traversed by something traveling slower than the speed of light, that's time-like. If you need to go faster than the speed of light to get there, that's space-like. The math all works out very, very well. But the fact that time has an arrow and space doesn't is separate from that. We can still imagine all that setup working, and yet nevertheless time didn't have an arrow. But for some reason it seems to, so we're trying to understand that.
Okay, because that confuses the hell out of me, because, wow, general relativity always confuses me. I guess that's why I like it. But what I understood, now I'm going to go way off here.
Okay, go way off.
In a black hole, I understood something like space becomes time-like once
Yeah.
you pass through the event horizon, or what, if it's something like that. And that means that the singularity becomes not a point in space, but it becomes the future, and that's why it's unavoidable. I couldn't
these are
quite
words.
follow the math. I
These are
sort
words
of, you know, but yeah.
you can hear, but they're not really true words. They're just very
Okay.
confusing poetic words. Space. What does it mean for space to become time? I don't even know what that means.
Yeah.
Inside the black hole, there is space and time, just like outside the black hole. The inspiration for that statement, that inside the black hole, space and time switch identities, is that if you put coordinates on space-time outside the black hole, so you have a time coordinate telling you what time it is, and you also have a distance coordinate telling you how far you are away from the black hole, okay? You're allowed to do that. You don't have to do that, but let's imagine you did that, and let's imagine that someone forced you to use the same coordinates inside the black hole. Well, it turns out that if you use the same coordinates inside the black hole, then what you were calling distance is now time, and what you were calling time is now distance.
Oh.
But it's only because you chose a dopey coordinate system to use, not because anything important happened with space-time. So the better thing to say, which is true and interesting, is that the singularity inside a black hole is a singularity in the future, not in the center. And that has nothing to do with coordinates or space and time switching. It's just a true fact that being inside a black hole is like being in a collapsing universe. Everything is smashing together, and the singularity is going to be in your future.
Yeah, that sounds familiar. Yeah.
Yeah.
I need to learn the math. That's the problem, I think.
You do. Yeah, that's right. I can recommend good books about that too.
All right. Womble, do you want to read out the chat room questions for me while I kind of get busy? There's a caller wanting to come in.
No problem. There was a question from Organic Beekeeper. I think I might have skipped one of the other questions, so I'll come back to in a moment. But Organic Beekeeper's question was, if time began at t=0, will it ever have an end point?
Yeah, again, we don't know. It's very, very easy to get right to the big questions we don't know the answer to. So just to be clear, we don't know that there was a t=0 when time began. That's an open question. We don't know whether there will be a t=t0 when time ends either. It seems very, very likely that there will not be an end to the universe. That's where the smart money is right now. When I was a graduate student, when I was your guys' age, we didn't know the answer to that. There could be an expanding universe forever, a universe that would eventually recollapse. They were all on the table. But in 1998, we discovered the universe is not only expanding, but also accelerated. It's expanding faster and faster. And the simplest models says that this acceleration will just go on forever. And if that's true, the universe will never recollapse. But it might not go on forever. There could be a phase transition. The energy density that drives the acceleration of the universe could change sometime in the future. So the honest answer is we don't know, although it seems likely that the universe will just last forever, which right there makes it very mysterious if it started a finite time ago. If there's 14 billion years in the past, that sounds like a lot until you say there are infinity years in the future, and then it seems very, very unbalanced. So that's a bit of a mystery.
Okay, thank you for that. I'm just going to scroll back up to the question that I skipped over by mistake. It's a question from one of the guests in chat, and it says, Roger Penrose, Rich God, Paul Steinhardt, Neil Turok all have infinity cyclical models of the universe. Are they realistic? Why do religious apologists insist that a cyclical universe/multiverse is contradictory?
Well, I like to think that my own model is realistic, yes. So I'm probably not the right person to ask. I am, again, very, very much on the side when it comes to these gigantic questions of the history of the universe. We just don't know the answer. It could be cyclic. My own model is not cyclic in the sense that things repeat themselves exactly, but it is eternal in the sense that the universe lasts forever toward the past and toward the future. In fact, I think that truly cyclic models, where things just repeat themselves, actually are very, very hard to make them work because of the arrow of time, because the past is so different from the future. As to the religious questions, I think that there's an interesting history here. One of the people who deserves most of the credit for putting together what we call the Big Bang theory of the universe was a Catholic priest, Georges Lemaitre, and he, was just being a scientist. He solved the equations that Einstein had given him, and he took seriously the fact that they predicted a singularity in the past. And now that we know that there's something called quantum mechanics, we know that you shouldn't take that singularity too seriously, but it's still there. It's still an event. And Lemaitre was very, very careful not to draw any theological implications from this. But it is tempting if you're theistically inclined. If you think that there is a moment that science tells you where the universe came into being, that kind of resembles a story where God created the universe at some particular moment in time. And Lemaitre was actually on an advisory panel to the Pope, and the Pope wanted to go out there in public saying, "See, science has shown that we were right all along." And Lemaitre said, "No, you don't want to do that," because he understood that as a scientific theory, the whole Big Bang model is always provisional. It's always ready to be improved. And if they had hung their hat on saying that the universe began at some moment in time, and 50 years later someone realizes, oh, actually the universe lasts infinitely long, he didn't want to let that be used against religious belief. So I think, I'm not religious myself, but I think the religious people who are making a big deal about the Big Bang are making a big mistake, because it's not that hard to come up with a story where God creates a universe that lasts forever, right? And you don't want to sort of let yourself open for that criticism for no good reason.
Brilliant. Thank you for that one. We have another question from one of our guests in chat. It says, I've got to make sure I say this right. The Feynman diagrams imply a sense of time travel. Would this be due to the statistical nature of entropy on the quantum scale?
Well, Feynman diagrams are a great thing. They're a way to keep track of what elementary particles are doing when they're scattering together. And they're a tool for theoretical physicists because you can actually calculate the probability in quantum mechanics of two particles interacting in a certain way using these Feynman diagrams. And I'm lucky enough to actually sit at the desk that Richard Feynman used to have at Caltech. So sometimes I will, slip blank pieces of paper into the desk, hoping that the next morning they will have lots of equations scribbled over them. But it has never happened quite yet. And there is an implication that Feynman diagrams come along with, which is that if you can have particles moving forward in time, that's equivalent to have antiparticles moving backward in time. But in fact, that's not saying there is an arrow of time. That's saying there's not an arrow of time. That's saying that whenever you have a Feynman diagram, you can flip it over, and the backward-going thing is just as good as the forward-going thing. That's opposite of our thermodynamic arrow time, where you can have things going one direction but not the other direction. So statistical mechanics applies to many, many particles. When you have, a coffee cup worth of stuff, or a person, or a universe, Feynman diagrams apply to very, very few particles, 2 or 3 particles coming together to do something and coming out in a spray of particles. So they're the opposite end of simplicity from statistical mechanics, where you have the arrow of time rearing its ugly head.
Okay, and we have a caller. Neo-Atheist, are you there?
Yes, I am, Troll. Thank you for having me.
No problem. Ask your question.
How does finding the Higgs boson change our understanding of the 4 forces of nature at the subatomic level?
Yeah, it's a good question. There are 4 forces that we've known about for a while now: electromagnetism, gravity, and then there's 2 nuclear forces, the strong and weak nuclear forces that only stick around at very, very short distances.
Exactly.
And then there's the Higgs boson, which we discovered last year. That's another book that you can all go out and buy that I wrote. I wouldn't say that it changes our understanding. I mean, it's crucial to our understanding, but the reason why it doesn't change our understanding is because it's been crucial to our understanding for 40 years now. We have the standard model of particle physics, which is this explanation for why the forces interact in the way they do. And the big mystery back in the 1950s was, why aren't the nuclear forces long range? Like electromagnetism is long range, gravity is long range. These are forces that are important in astrophysics, also in your living room, right? But the nuclear forces are only going over very short ranges. And so it turns out that the strong and weak nuclear force are short ranged for 2 completely separate reasons. And the strong force, because of what we call confinement, the strong force is just so strong that it can't leak outside a proton or a neutron or whatever. And the weak force, it's the Higgs boson that is to blame. And this was the picture that we put together in the 1960s, that if empty space is full of this invisible energy field called the Higgs field that can act like fog on a cloudy night where you can't see things very far away. Likewise, the weak force can't stretch very far because it's absorbed by the Higgs field in empty space. So what we did last year was to verify that that picture was correct. But that picture is from the 1960s, and we've more or less believed that that picture was correct since at least the 1970s. So what it really just means is that we're on the right track as far as understanding those four forces of nature. We want something surprising, right? We want something new and unexpected to come out, but the LHC hasn't quite given that to us yet.
Now, with that, with the Higgs boson field and us actually coming closer to actually understanding it at its most finite level, how would that actually affect quantum entanglement? Or understanding of quantum entanglement, at least.
Yeah, I don't think it affects it at all. Again, particle physics is a very crucial part of science, obviously, but it really focuses in on the simplest stuff, right? That's why you can make a lot of progress in particle physics. That's why physics is the right major to choose for scientifically minded people with short attention spans, because there's only a few moving parts at any one time. Entanglement requires very, very carefully set up experiments where you have one quantum system entangled with another, and then you take them and you spread them out over large distances, and you can do things with them. It's crucial to how nature works, but again, we've understood it for a long time. The discovery of the Higgs boson hasn't changed our understanding of that in any significant way.
Okay, anything else, Neil?
That's basically it. Thank you for having me on, Troll.
Yep, it's a pleasure to have you on. Okay, Marty, do you have anything to come in with there?
No, not regarding that, but I can move on if you want me to.
Yep.
We did have another question from Tat.
All right, yeah, well, go with the chat room question and then go with Marty.
Go ahead.
Okay, it was from one of the guests, so we don't have a proper username for them. It says, what is your opinion on Freeman Dyson's assertion that the universe manifests qualities of a mind? What about his stance on fine-tuning?
I don't know exactly what Dyson's stance on fine-tuning is, so I can't speak to that unless I know what the claim is.
That might have been your stance on it, I think.
My stance? I definitely have my own stance. Yes, that's right. So let me ask the first question first. Answer the first question. Does the universe manifest the qualities of a mind? I mean, that's kind of too vague to be very strongly opinionated one way or the other. I'm certainly a naturalist and a materialist. I think that the universe is made of stuff that just does its little stuffy stuff things. And things like life and consciousness emerge out of the inorganic, unconscious motions of stuff in the universe. And I think it's a fascinating question about how that happens. As computers get better and better, as you can talk to your iPhone now and have it give you directions and stuff like that. And computers get better and better at mimicking everything that living beings do. I think it becomes harder and harder for people to pretend that there is anything truly special about collections of atoms that we call conscious beings, as opposed to collections of atoms that we call anything else. So I think that it's not that the right interesting way to think about it is not that the universe is like a mind, but that the universe has sufficient richness and complexity inherent in it that it can lead to things like minds. And I think that's, we're lucky that that is true. And that's a very interesting characteristic of it. As far as fine-tuning is concerned, I mean, there is fine-tuning in the universe from our point of view. Something that we think is finely tuned from our current perspective is probably just because our current perspective is not good enough to give you the final answer. The value of the energy density of empty space is much, much smaller than our naive theories would predict. The mass of the Higgs boson is much, much smaller than our theories would predict. Are there reasons why? I mean, it could just be an accident. It could be environmental selection, that there's many different parts of the universe with many different values for these parameters. So I think that, we don't know that there is fine-tuning in a fundamental way. We know there's apparently fine-tuning. We don't know whether it will go away, so it's a good clue to physicists trying to figure out the universe, but it would be very, very wrong-headed to take it too seriously as something that is absolutely intrinsic in how nature's arranged.
Okay, Marty, you had a question there.
Yeah, I was just gonna move on to the next point I had. M theory. What's your take on that? Because I understand a lot of different physicists have different ways of looking at that. Like some think it may not be the holy grail of physics, but it will be, and others say it's pretty much pseudoscience or borderline pseudoscience. What's your take on it?
It's certainly not pseudoscience or anything like
No.
that. That's kind of unhelpful griping from people who are past their prime. There's a history here. In the 1970s, particle physicists put together the standard model of particle physics, and for better or for worse, the standard model has worked since the 1970s. That is, with a tiny exception of the mass of neutrinos and maybe dark matter, every experiment we've done here on Earth has been absolutely compatible with the standard model of particle physics. And therefore, it's hard to move forward because you don't have any evidence of anything beyond your current understanding. However, there's one thing that does not fit into that understanding, which is gravity. So in the 1980s, physicists became increasingly interested in tackling the hard problem of quantizing gravity. It's just a natural thing to do. We don't yet have a theory that completely reconciles gravity with quantum mechanics. And what they realized is that this theory that had been around for quite a while, called string theory, offers a very, very promising way to help quantize gravity. When you start trying to marry together gravity with quantum mechanics, certain things just go wrong from the start, and string theory fixes them in a very promising way. And furthermore, they realized there was only 5 different ways to do string theory. There's only 5 different fundamental string theories, which sort of narrows down the space of possibilities by quite a bit. Then in the 1990s, there was a good news and bad news situation. For one thing, they realized that these 5 different string theories were not 5 different theories. They were all 5 different versions of the same underlying single theory, which is called M theory. So that was good news. In fact, there's only one theory, we think, that really fundamentally works to make a universe that looks like ours. The bad news is that there's many different manifestations of M theory. When you have M theory predicts there are all these extra dimensions of space. We don't see them, so they have to be curled up and hidden from us somehow. And there's some ginormous number of ways to curl them up and hide them from us, as far as we can tell. And they all end up giving you local laws of physics that look utterly different. So if you want to use M theory to predict the local laws of physics, like the mass of the electron, the mass of the quarks, the strength of the electromagnetic interaction, M theory turns out to be useless because there's many, many different possibilities. So the good news is that it's a promising way to quantize gravity. The bad news is that it's almost inconceivable that we can make a strong prediction using it. Now, that may be because we just don't understand it very well. The data are not pushing us in one direction or another, and without data, physics is much, much, much harder. But it's still the most promising way to quantize gravity. So I still think that it's very, very worth taking seriously how M theory works and trying to connect it to the real world.
Okay, Wombo, I think there's a few chat room questions coming.
Okay, yes, there was one just now. Let me scroll so I can read it up on the Skype. It said, oh no, that's the wrong one. No, where was I can't find it. I've lost it. No, that was the last one.
All right, there's
Have
one
I seen
just
another
there.
one?
There's one just come in there. So
Where is it?
just come through in the chat.
Oh, brilliant.
Yeah.
Yeah. Okay, so it's from another one of our guests, and it's directed to Sean, and it says, is inflationary cosmology the only game in town, in commas, quotation marks even, so to speak, or are there other viable theories about the beginning of the universe?
Well, that's a good question. It's a very, very pertinent question right now. Inflation is this idea that came out in the early 1980s, that if you start the universe in a tiny little patch dominated by what we call a false vacuum energy. In other words, if this little patch is not full of particles bubbling at a different temperature, but it's just a smooth patch of energy, then it can accelerate and expand by an enormous amount and then convert into ordinary matter and energy and leave us with a very hot, dense, smooth, rapidly expanding universe, which is what we had in the early universe, a hot, dense, smooth, rapidly expanding phase. So you can get a universe that just looks like our early universe out of a very simple starting point. And since then, there's been no better model that has come along, certainly, no more promising alternative. And so many working cosmologists take inflation for granted. They assume that inflation must be right because it more or less fits the universe we see, and the theorists have failed in coming up with an alternative that does just as well. On the other hand, also we discovered there are problems with inflation. Number one, getting this initial starting patch of a smooth patch of space is much harder than people originally thought. We don't know how to do that in the first place. Number two, once inflation starts, it seems like it never stops. So instead of giving rise to only our universe, it gives rise to an infinite number of universes that all look different from each other. So instead of predicting uniquely that you should get a universe that looks like ours, it predicts some statistical ensemble of many different universes, and then you have to sort of talk about the probability that our universe looks one way rather than another way, and those probabilities seem to be completely ill-defined. So inflation is still the best game in town. There's no good alternatives. There are attempts, but I would personally say that they're not very good right now. So there's still the looming possibility that there is a correct alternative we just haven't thought of yet. But other than that, inflation, is still the thing that most of us work on.
Okay, Womble, there's another one there.
So the question is from another of the guest members in the chat. It says, what are Sean's thoughts on the recent black hole debate, which brought up complementary firewalls and Hawking radiation?
Yes, good. I like this. Someone who's been reading out of school, obviously. So black holes have been around for a long time as a theoretical idea. And of course, in the 1970s, Stephen Hawking said that they're not completely black, that black holes give off radiation due to the effects of quantum mechanics. And this is a huge, central idea, even though it's just a thought experiment. We've never seen a black hole radiating like that. But it's really the best thought experiment laboratory we have for understanding quantum gravity. So people put a lot of thought into it. And one of the difficult questions has been, if you throw an encyclopedia into the black hole, and then the whole black hole evaporates away, is the information that was contained in that encyclopedia somehow implicitly contained in the radiation that came out of the black hole, or is it destroyed? The information loss paradox. In ordinary quantum mechanics, if you take an encyclopedia and set it on fire so that it burns and it goes away in heat and light, in principle, if you collected every little photon of light coming from that fire, you could reconstruct the encyclopedia. In practice, it's too hard, but in principle, you could do it. Is that true for black holes or not? And this has been an ongoing debate for a long time. And recently, just last year, a collaboration known as AMPS, I'm going to forget their names, but A, M, P, and S are their initials, made a claim that if information is conserved, then when you fall into a black hole, it's not just that you pass through the event horizon and eventually hit the singularity inside. It's that when you think the event horizon is there, the boundary of the black hole, you are actually incinerated by a wall of fire. And this is completely contrary to everyone's intuition about how black holes work. So this is now known as the firewall puzzle or the firewall paradox. When you fall into a black hole, do you just pass peacefully through, or are you burnt to a cinder? And honestly, I don't know. I think it's a very good question. I think that we're dealing with the fundamentals of the setup are things we don't understand very well. We don't understand what the space of states of a black hole is in quantum mechanics and so forth. So we're really sort of fumbling around for what the basic rules should be. And I think that the proposal that there are firewalls will be very useful in figuring out what those basic rules are, but I'm not going to bet right now one way or the other what the truth actually ends up being.
Okay, Womble, you had a question there?
Yeah, it's kind of on the back of that. It's based on something I read a few years ago now. I read a book by a popular science author called John Gribben. It was his Almost Anyone's Guide to science. And towards the end of the book, he was talking about some speculation that was floating around in sort of some physics circles, that potentially what might be happening is that of black holes, on the other side of them, you've effectively got some sort of big bang forming, and that potentially you have a new universe forming on the other side of the big bang. And I was just wondering if you thought there was any validity in that, or if it was just a bit of kind of blue sky thinking, as it were, for physicists.
Well, there's a couple different things going on. It is conceivable that that our universe can pop out a new universe, that there can be baby universes, that our universe can give birth. And what that would look like from the outside is that a black hole had formed and then quickly evaporated away. There would not be an umbilical cord that remained attaching us to the baby universe. The umbilical cord is cut very, very quickly, and from the outside it looks like a black hole. On the other hand, so that's very speculative. It may be true or may not be true. We honestly don't know. There's also the question, is that usually what happens when you make a black hole? So not just when you make a baby universe, there's a black hole, but every time you make a black hole, there's a baby universe. And that way seems much harder to justify. There's no evidence at all that when you make a black hole, there's usually a baby universe on the other side. It's possible. Many things are possible. It's, again, we're right at the edges of things we don't understand. But no one has a model in which that works or anything like that. So I would keep it on the shelf as an open-minded possibility, but it's not as if that's something most people think is true.
Brilliant, thank you.
Okay, there's a chat room question, but there's one thing I wanted to speak to Sean about. As I've heard, you work as a movie consultant for getting science right in films. So can you give us a kind of brief kind of overview of what that involves really, and what kind of stuff you've contributed?
Yeah, it's very interesting because obviously the science that you see in many Hollywood movies is terrible. Everyone admits that, including people in Hollywood. And all else being equal, usually they would like to get it right. By they, I mean the directors, the producers, the writers in Hollywood, the actors. They try very hard to get other things right, if some historical drama or something like that. But of course, they will always sacrifice any bit of historical, scientific, psychological accuracy for telling a good story. So what you need to do as a scientist, if you get an opportunity to talk to someone in Hollywood, is convince them that they can tell a better story by getting the science right than they can just by making shit up and having whatever they want occur. And you can, because science is interesting, because all of movies are about drama. They're about limits. They're about things you can't do and obstacles that are in your way. And the laws of physics are a big set of obstacles that are in your way. They attempt to work within a logically consistent framework where the rules are clear is much more interesting than working with a framework where anything can happen, and then it's not a lot of tension there if anything can happen. So that's the pitch you need to give to the people who are making these movies, and often it works. So it's a very, very incremental process. It's still true that most people in Hollywood are completely oblivious to science and like it that way. But there's an increasingly influential cadre within Hollywood that says, look, you can make a more interesting movie by talking to the scientists and getting some ideas from them. And it's incremental, like I said, but in Thor, in the movie from Marvel Studios, Natalie Portman's character is a physicist, and in the comic book she was a nurse. And she herself has said in interviews that she hopes that some 12-year-old girl is going to see her in Thor playing a physicist and go, that's something I could do as a living. And things like that are have a much more noticeable impact than all the public talks and books that I could ever write.
Okay, I just want to ask, in your personal opinion, what's the kind of major offenders movie-wise of just horrific science? Is there is there just one that sticks in your mind?
The things that I mind are not violations of the laws of physics, because you're not going to make Thor and pretend to obey the laws of physics. Okay, that's just obvious. What bothers me more is when it's obvious the movie could have been better if they had made a little effort to get the science right, and they didn't make the effort. So the example that I use is a little bit unfair, but I use the example of the Star Trek reboot movie, the J.J. Abrams movie from a couple years ago.
Thumbs up.
Absolutely.
I don't like what they did to the core of the planet. I'm a geologist.
Yeah. And again, it's not because it violates the laws of physics. It's just because it wasn't explained. Why do they need to do this? What is this stuff? What is the danger? What can I do to prevent? And it makes the movie less interesting to me. If I know what the stakes are and I know what the danger is, then I'm invested in what the characters are going through. Where if
it's inconsistent as well.
And then that's not as interesting.
It's inconsistent as well because in the beginning it's established that black holes send you back in time. But then Vulcan didn't go back in time, it blew up. And in the end, the ship blows up.
No, you see, this is where I'm going to nitpick you, because in the beginning it was they launched the red matter at the supernova thing, and so the time travel it was the combination of the red matter and the supernova.
Nerd rage.
Here we go.
Yes.
I'm a geek, thank you very much.
Okay.
Okay.
All right, we do have a caller, but there's a very quick question from the chat room, and it's from Neo-Atheist who called in earlier, and he's wanted to know how much closer does finding the Higgs bring us to quantum computing?
Yeah, again, I got to be disappointing. Finding the Higgs does not have any technological applications whatsoever, roughly speaking. When you make the Higgs boson, number one, just to make it, you need a $9 billion particle accelerator, 27 kilometers in circumference, moving at ultra-high speeds, protons moving in it. It's not a back of your pocket kind of device. It's not a tabletop experiment. And number two, then you smash those protons together at 99.999999% the speed of light. And usually you make just a mess. Very, very, very occasionally you make a Higgs boson. And then that Higgs boson decays in 1 zeptosecond, 10 to the minus 21 seconds. So the Higgs bosons don't hang around for us to do things with. We don't even see them. We just see what they turn into when they decay. Yep. Can you still hear me?
Yeah, we can. Sorry, that's the caller. Caller, can you just hold on while Sean finishes his point?
Yeah, sorry, sure.
Yeah, no problem.
So, so the Higgs boson is going to teach us about the laws of nature at a fundamental level, but they won't help us do anything in terms of making a computer, quantum or otherwise. Quantum computers are small, and we try to keep them at low temperatures, but they're still with atoms. All of the technology is going to be atoms.
And hello, and welcome in our caller. Seth, are you there?
Yes, I'm here. Can you hear me?
Yep, no problem. Ask a question for Sean.
Oh, hey, Sean. It's a great pleasure to be able to ask you a question. My question is about the inherent randomness in quantum mechanics, and as an amateur, I'm a little confused because I've heard Lawrence Krauss recently in a debate say, "Look, you guys don't understand. The partial differential equations that explain quantum mechanics are completely deterministic." And yet, on the other hand, I've heard physicists say, not only do we, it's not just the case that we don't know whether quantum mechanics are random, we know for a fact that it's random, that there's something non-deterministic about it. Could you speak to that and maybe clear up whether the randomness is inherent or whether it's just that we don't know enough?
Yeah, so again, a great question. This is another one where we don't know enough because this is the famous, what we call the measurement problem of quantum mechanics. The reason why quantum mechanics is mysterious is because if you open a textbook that is supposed to teach you quantum mechanics, it says that a quantum mechanical system behaves in two completely different ways depending on whether or not you're looking at it. If you're not looking at it, it evolves deterministically. There's no randomness. Everything is smooth and predictable and reversible. If you observe it, then it's random. The answer you get from that observation is just an unpredictable throw of the dice. I mean, you can predict the frequency. You can predict that you'll get a certain answer a certain percentage of the time and a certain other answer a certain other percentage of the time, but you can't reduce those uncertainties to certainties. And so this is a mystery. Why in the world does the world care if we're looking at it or not? Very, very few people think that it's actually because we're looking at it. There's certainly something else going on. So there's roughly speaking two possibilities. One is that secretly everything is deterministic, but our path through the universe is not seeing the whole universe. So this is what we call the many worlds approach to quantum mechanics, or the Everett approach to quantum mechanics, and it's the one that I believe in, that actually the actual underlying laws of physics are perfectly deterministic. There's no true randomness, but what there is branching, that there's a U who does a quantum mechanical experiment where their electron is over here or over there, and before you do the experiment, there's one you, and after you do the experiment, there's one you that saw the electron over there, and another you that saw the electron over there. There's now two copies of you. And the evolution is perfectly deterministic, but it's evolution from one copy of you to two copies of you. So both of those copies in the future think that something random has happened. The other possibility is that there really is true randomness somehow. Nobody has any great ideas about why that's supposed to be true or how that's supposed to be true. You can do some mathematical models which fit the data perfectly well and are consistent and complete. They're ugly, they're ad hoc, and there's no reason for them to be right. But we don't know for sure. I personally strongly believe that even though it's a minority point of view right now, the many worlds approach to quantum mechanics will take over. Everyone will agree with it down the road, and then the randomness will only be apparent. It will not be fundamental.
So effectively, Sliders is true.
I didn't see Sliders, so I don't know. But certainly there's a lot of room for good Hollywood movies about the many worlds interpretation of quantum mechanics. Let's say that.
Any further questions, Seth?
Well, yeah, one quickly. Does that have anything to do with the fact that we always hear that radioactive decay is inherently random? Is that non-random on the Everett model, or is that a completely different subject?
That's exactly right. In the Everett model, there is a wave function that describes the possibility that the nucleus has not decayed or that it has decayed. There's a smooth evolution between one and the other. And depending on when you interact with that nucleus, there's different copies of you that saw it decay at different times.
I see.
But everything's reversible, yeah.
Thank you very much. A bit fascinating.
All right.
Sure.
Thank you very much, Seth. Thanks for the call.
Thanks, guys. Great show.
Okay, Marty or Womble or Kitch, questions?
Yeah.
Yeah, okay. We'll go with Kitch. You've been quiet.
Sorry, just a little bit outside my knowledge base, but so this might be a dumb question. But,
Finally, good.
Dumb ones can sometimes give the really best answers.
Yeah.
Okay. What do you do you think that Earth will be the only planet with intelligent life? Or do you think that intelligent life is so rare?
I've heard dumber questions than that, but no, I mean, this is obviously a crucially important question. The big news is that in the last 10 years, the idea of other planets has moved from speculation to complete reality. We know thousands of other planets out there in our galaxy right now. And my personal point of view is that this is incredibly interesting and awesome, but should not have been a surprise to anyone. We should expect that there should be billions of planets in our galaxy. Some of them will be roughly Earth-like. Some of them will be very different. Again, that's not a surprise. So you take a large number of planets, you multiply by the probability that life forms on any one planet, and you multiply that by the probability that when life forms, it becomes intelligent. Now, those other two numbers, we have no idea what they are. What is the probability that life forms? We have no idea. What is the probability that life becomes intelligent? We have no idea, and I just refuse to listen to anyone who claims to have an idea about that, because there's just so many uncertainties that we don't know. All we know is that we're here, and that gives us nothing, zero information, because if we weren't here, we wouldn't be talking about it. If we discover one other example of life having originated on another planet, that's an enormously larger amount of information. So we should be trying to do that everything we can. I would not be surprised if life were ubiquitous. I would kind of be surprised if intelligent life were ubiquitous, not because I think intelligence is something special, but just because it would have been easy to notice by now if intelligent life were ubiquitous. But that could be very, very wrong, because it could be that we're very parochial, right? We think that what intelligent civilizations do is spray radio waves out into the universe and then send out rockets and so forth. Maybe what intelligent civilizations do is upload themselves into computers and then die. We don't know, you know? So I think this is absolutely an empirical question. We don't have the theoretical knowledge to make a good prediction, nor do we have the data to draw any conclusions. But that is changing on both fronts. So it's a very, very exciting topic to be thinking about these days.
Okay, and I think, Marty, you had a question.
Yeah. What's your take on the Lawrence-Krauss hypothesis I wrote here? The idea of the universe coming from nothing. I guess it's kind of after hearing what you said earlier about you believing the universe to be eternal. I guess it doesn't really mesh very well with that. But could you?
Yeah, I think
talk about that a little?
Just like the religious people, I think that we science people should not pretend to know the answer when we don't know it yet.
Yeah.
The universe could have come into existence at some moment in time. It could have, quote unquote, come from nothing. I don't think that answers the long-standing philosophical questions about why there is something rather than nothing, because you still need to understand why there are the laws of physics that allow universes to come into existence. And we have no idea what the answer to that is, and there might not be any answer to that.
It might not be a meaningful question, right?
Yeah, exactly. It might not be a meaningful question. It might not be the kind of question to which there are answers. So the possibilities are both on the table. I suspect myself that I would bet at even money that the universe is eternal, that time lasts forever. Space might not be eternal. What we call geometry and particles and things like that, these are all classical notions, right, that we know are just an approximation to the true quantum mechanical underlying reality. And so there might be times in the history of the universe when there was a universe, but there was not space or particles or matter. That's very plausible to me. But right now I'm just open-minded about how that is supposed to work. I don't think that we are close to the right answer about that, which is fine. We have no data. It might be 10,000 years before we figure this out, but we're at least moving forward in the right direction.
Yeah. Okay.
There is a question. It's quite a simple one from the chat, but it is quite one that's quite interesting. What are black holes made of?
That's good. Black holes, if you want to be careful about it, are not things in some sense, right? They're regions of space. They're regions with the property that once you enter that region, you're not going to leave. That's what a black hole is, that once you enter the event horizon, you can't escape back to the rest of the universe. It's a one-way ticket inside the black hole. Except, of course, that black holes evaporate and give off radiation, but it's not you who will be leaving in the radiation. It's your cremated remains that will be leaving in the radiation. So what are they made of? Well, you create a black hole in some way, and there's many different ways to create it. Anytime you get enough stuff into a sufficiently small region of space, you make a black hole. So that could happen in the early universe through quantum fluctuations. It could happen through stars collapsing, and it could happen at the center of galaxies. And we know at least the latter two examples actually do happen. So there are sort of two kinds of black holes that we know are abundant in the universe. There are stellar mass black holes, 10 times the mass of the sun, where a giant star has collapsed and formed a black hole. And there are supermassive black holes at the centers of galaxies, millions of times the mass of the sun, where many, many different stars have collapsed because things are so dense there at the centers of the galaxies. But once they've collapsed, it's not right to say that the black hole is made of that star or that collections of stars. The black hole is just a big collection of gravity, right? That's what it is. It's a very, very strong region of gravitational field that sucks you in and then you can never leave.
Okay, Womble, I think another chat question and then we'll go to Kitch after that.
Okay, this one's from the Neo-Atheist, and it says, does finding the Higgs bring us closer to finding a way of going faster than the speed of light?
Right, so the answer is no. The Higgs does not, well, so I hate to say it over and over again. There's two big looming sad facts. One is that discovering the Higgs boson hasn't really taught us anything at all that we didn't already know, except the mass of the Higgs boson. Because the theory of the Higgs boson was already in place since 1964. Really, since 1967, Steven Weinberg showed how the Higgs boson could play a role in what we call the standard model of particle physics. So the discovery of the Higgs boson has so far simply taught us that that theory from the 1960s is right. That's what we already suspected was true, so we verify that that is true. What we're hoping is that as we study the properties of the Higgs boson, it will begin to deviate from the 1960s predictions, and then that will actually be teaching us something brand new. You know, the Higgs boson decays into different particles, like decays into photons, decays into quarks, decays into gluons, and the theory predicts the rate at which all those different things happen. So if any one of those rates deviates from the theoretical prediction, that will be an enormously important discovery. But none of it is going to help us moving faster than the speed of light, because you can't move faster than the speed of light. That's what Einstein said, and he was true. He was right.
Okay.
That will remain true.
All right, Kitch, you had a question ready.
Yes, I was just wondering for that when you entered the event arising, even light can't escape. Yet the black hole emits radiation. What exactly? How can the radiation escape? What's so special about this emission, the radiation being emitted, that it can escape, but other things cannot, that enters the event horizon?
Yeah, this is a great, very good question. This is why Stephen Hawking is a genius, right? Because he figured it out. Because before he came along in the 1970s, everyone assumed, believed strongly, with good reason, that nothing could come out of the black hole. And really, sort of the answer is that even in Hawking radiation, nothing is coming out from inside the black hole. The radiation comes out from just outside the black hole. The quantum mechanical vibrations of elementary particles just outside the black hole escape as Hawking radiation. And the right way to think about it is that you create two particles. You create sort of a particle and an antiparticle. And this happens all the time in empty space. All around you, in front of your nose, there are particles and antiparticles coming into existence. But if they're right next to a black hole, the particle can escape and the antiparticle falls in. And if you sit down and calculate the energy, the amount of energy carried off by the particle escaping is balanced by a negative energy falling into the black hole. So when we say the black hole evaporates and loses mass, it's not because something is going from inside to outside. It's because negative mass is falling into the black hole. And obviously this is a little bit disconcerting, but this is the implication of the math that Hawking worked out in the 1970s.
Okay, okay, there were some chat room questions, Womble.
Yes. Oh, sorry about that. Start again. The next one is from one of the guests in the chat, and the question is: eternal time in the past, or only from a single point in the past and eternal into the future? I think the question's about whether or not time's going to be infinite. Looking at it.
Yeah, I think. All these options are on the table. It is possible that time is finite toward the past and infinite toward the future. It is also possible that time is finite in both directions or infinite in both directions. It is, I guess, possible that time is infinite toward the past and finite toward the future, but nobody believes that. If you want to stake out a minority position that no one else believes, think that time is infinite toward the past but will only be finite toward the future. We're trying to figure this out. We don't have the right theoretical tools because we don't understand how gravity and quantum mechanics play together. And that's what you need, because in the early universe, what we call the Big Bang, it's prediction of general relativity, there's a singularity. But general relativity is a fundamentally classical theory, which is to say it doesn't include the insights from quantum mechanics. And at a moment like the Big Bang, when there's enormously high energies and enormously high densities, the insights from quantum mechanics are obviously going to be absolutely central. So the fact that there was a Big Bang, a singularity, doesn't mean the universe came into existence then. It means that the classical approximation to the behavior of the universe fails at that point. And we just don't know what happened earlier than that. If you forget about general relativity, forget about gravity, forget about cosmology and all about that, and just look at quantum mechanics predicts very unambiguously that time lasts forever. You know, there's no beginning or end of time in quantum mechanics. So my suspicion is that we will need to fit general relativity into the model of quantum mechanics rather than the opposite way around. We will eventually learn that the universe lasts forever.
Okay, Womble, I think there's some more chat room, unless Mortimer or Kitch, do you have follow-up questions? Or go to the chat
Well,
room?
yeah,
Okay.
while on the subject of eternal time, I don't know if this is gonna be science or philosophy because they're both try to talk about time. But this whole idea of A time and B time, is that something you're familiar with?
And we've lost
he
Sean.
just disappeared.
Okay, well, so what did
That's not good.
No, it's not good. It's not very good at all. Sorry, everyone.
No, it is not.
You have lost Sean. Yeah, like someone said, he's been quantum tunneled away from us. And we've now lost Womble as well. No, this is going...
I think one of the trolls has taken us out one by one.
Yes. There have been a lot of them tonight. Marty, suppose I'll just ask you...
Womble actually left. She wasn't
okay, that's no
disconnected.
problem. So Marty, while we get Sean back, tell us a little bit about your new video, the spirit science.
Yeah, you sent me to that channel.
Yeah. So what was it about that
a week
video?
ago, and it was. I had a little to drink, and I wanted something stupid to laugh at, and that was just perfect because it was so hilariously stupid. It's this new age bullshit channel called the Spirit Science.
Yeah.
And I just decided to start by looking at the first video of the. I don't know if it was the first video uploaded to the channel, but it was the first video of the series that's going on there, simply called Spirit Science. And, well, go watch it. That's basically it. It's the usual stupid new age nonsense. About how we can think happy thoughts and miracles will occur.
So the thing that always gets me about that, they say think happy thoughts, and they will does the same go for thinking bad thoughts? If your thoughts become...
that's what they think.
They never seem to elaborate on that. Like if I start thinking get rid of all the trolls in our chat room right now, that's... No, I don't know if that's positive or negative, because some of them are entertaining us right now. And as we try and get Sean back right now, we're just desperately trying to fill in some airtime with us. So, chat room, if you've got any questions for us right now, while we get...
How about a musical number?
Yes. So, Kitch, I think we might as well ask you about give us some news about nanoparticles, why they're so awesome.
Well, we were what I don't know. I don't know what to say.
Yeah, you just work on them every day. That's all.
I work on them. Well, I work with them in bacteria every day. I just don't know. I just got been put on the spot. They're awesome because silver is great. Yeah.
So, like, what's the potential benefit of nanoparticle research?
Well, different. Depends on the particle. Like gold has many uses in medicine, environmental cleanup, optics, electronics.
Yeah. So, I'm going to ask you. Sadly, we have to bring this name up again, Mike Adams.
Oh God, no!
So, yeah.
Oh.
So, no, it's just to clarify. Like Mike Adams, he's always on the nanoparticles cause cancer. Is that true or not?
It depends on the nanoparticle. The nanoparticles are so broad and, like it's like saying compounds cause cancer.
Chemicals cause cancer.
Yeah. You have to really define which ones.
Yeah.
Gold is relative. Gold is not really cytotoxic or carcinogenic.
Yeah.
Silver is okay. Titanium dioxide depends on where it gets to it, and it's also depending on where you're putting it as well. It's like saying, this compound could cause cancer if it gets into the heart, but you're just using it as. Sorry, that's a long day. It's also about where you're defining it. If you're applying something to the skin, but if you're applying something to the skin, then it's fine. If it doesn't, if it doesn't travel into the skin and go into the bloodstream, then you're fine.
Yeah.
Like I think titanium is fine in terms of sunscreen. Also, you also have to realize that you also have dose as well. There's an awful lot in it, in this than just it causes cancer. You need to say how much of it causes cancer. How much do you need to get an effect? Where does it cause the effect? Because different cell lines will have different sensitivity.
Yeah.
For example, in the epithelial cells of your lung, there will be a lot better adapted to oxidative insults because it's very it's used to getting oxygen and all these kind of environmental impacts. But if it won't be as maybe as sorry. I hate being put on the spot,
So,
but
yeah. So, like, where does this general, like, the hysteria that nanoparticles cause cancer? Where does that originate from? Is there like a is it just like some research paper they misquoted or something?
I'm not too certain, to be honest. I think it comes from studies where they say they have an effect. They'll test it on a cell line and they say, we've got damage, or we've seen what the effect of, we've seen some effect. But at the same time, you're dealing with one cell line, and it's not even sure if the nanoparticles will make it to that cell line.
Yeah.
You need a much better model.
Mm-hmm.
And cell lines are the great first step. They can show you that, if your nanoparticles get here, it will have this effect, but they still need to go on to a system, like a more complicated system, because there are more, you're dealing with, in the human body, you have many cell lines, with many different phenotypes, and they all interact, and they could make it better or worse. For example, if you put on, let's just say, this is a hypothetical, but I will explain it better. If you have a cell line of epithelial cells and you grow bacteria on it, you're going to see a lot of killing. Now, that bacteria may be harmless, in humans, it might be just a common cold. And you see that a cell line, let's say if you incubated an aerated epithelial cell line with rhinovirus, you're going to see an awful lot of killing. But if you get a cold, you're not going to die.
Yeah.
It's harmful, it's not terribly great for you, but it's the most horrible thing you can get. Although I have put up on the TWL blog an essay I've done about the common cold and how it may not be as harmless as we think.
Yeah. We're still having difficulties in getting Sean back. I'm trying to message him.
Yeah, is he online?
Yeah, he shows us online. I've messaged him. He's not getting back, so it could be anything.
It's probably just.
Yeah, it is probably, because I think his connection was a little bit off at times. So we'll just wait and try him back. Yeah. So I do have.
Hopefully.
And well, again with you, Kitch. Sorry we're just trying to film, but you've got a new video series coming up. I helped you with a trailer for that, so. Give us a little bit of it. This is it's a subject you love, so give everyone like a little taster of what this video series you're doing is going to be all about.
Well, I haven't decided on the format just yet. I'm teasing out some things, but I'm hoping to do a video series on different bacteria, introducing different bacteria genus. My first video is going to be introducing Shrinella and introducing what it's about, how we can use it, and other different research topics on it.
Yeah.
For example, Shrinella is used in bioelectrochemistry experiments, nanotechnology. And then I'll be going through it like E. coli, Pseudomonas. Actually, I'm really looking forward to the Pseudomonas video because that's a very important bacteria in terms of medicine and the environment.
Yeah, and of
And
course,
biofilm.
and of course, there's the celebrity of the bacteria world, E. coli.
Yeah. Yeah, that'll be an interesting one as well because you have so much to do on that because
Yeah.
you've got like the great things out of it, like genetics research, recombinant DNA technology, evolution,
Yeah.
and stuff like that.
Well,
And it's also used in toxicology studies, and also, of course, it's also its darker side,
Yeah.
the 0157.
yeah. Like I say, it's been used a hell of a lot in widening our understanding of evolution, hasn't it, E. coli?
Yeah. Because it just grows so fast. For example, for a human generation, it takes, 20 years
Yeah.
for every generation. For bacteria, it takes about 20 minutes.
Okay, well, I do have something we could comment on, and sadly it is Mike Adams again. But he has a prediction for this week, so we can all keep an eye out. He says this... Right, so I'm going to say, this is a short but urgent warning. A false flag event, an act of war, a bombing, or some other headlines-grabbing orchestrated event is very likely to occur in the next 7 days, precisely because the Obama administration is under intense fire right now and needs a quick distraction. So that's going to be one of these, anything that happens, he's going to call it, that's it, isn't it? Any news story in the next...
I bet you he's going to say it's Alex Ferguson retiring.
It's just... But I think Sean is trying to call me, so we'll try adding him.
Grand.
No, he's not there. So yeah, a quick word on that story, Marty. Apart from you slamming your head into the desk again.
He's an idiot. It's that simple.
No, well, I don't actually think... See, I think Alec Jones is an idiot, but Mike Adams is insane. If you read a lot of his blog
posts... Yeah, he may be insane too, but he's definitely an idiot.
Yeah.
Mm.
But whereas I think like Mike Adams is dangerous, and...
Yeah.
Like I said, if you read a lot of the things, it's the rantings of a madman at times. Yeah. I mean, you saw that article that he made about he wants this fair new society where only 5% of people would vote.
Yeah.
And he said...
And of course, only the 5% that he approves of.
Yeah, and he said he would even allow gays to vote, because he's such a nice guy.
Yeah, because they currently can't vote, right?
Isn't he merciful?
Okay. Hello, Sean.
I'm back.
Hey!
Hey.
That was some of the most kind of improvised stuff we've ever done. Welcome back, Sean.
I hope that you continued on the conversation.
Well, we just kind of went into... We were just actually getting into talking about Alec Jones and conspiracy theories before we got you back.
I'm no good at that. So.
Okay, and I think... right, Marty, did you have a question before we lost?
Yes, I did have a question about, especially when you brought up time being infinite, this whole thing from philosophy where they have A theory and B theory of time. How does that fit into this? Or is it just a case of philosophers need to stop meddling with things that are actually physics? Or what's your take on it?
Yeah, I don't think it's philosophers meddling. I mean, the philosophers are very good at setting out the space of all logical possibilities.
Yeah.
And it's up to scientists to figure out which one is right. I'm seeing the video. Okay. Can you guys see me, by the way, and hear me?
You're frozen, but we can hear you, so that's fine. Oh, it's what you're moving again.
So the roughly speaking, the A theory says that now real and the past and future are not real, and sort of our moment of the now is moving through the past and future. And the B theory says that all moments are equally real, and they're not real at the same time, because that doesn't mean anything, but they're equally real, and we are experiencing the different moments personally at our own different moments in history. And the physics comes down in favor of the B theory, that all moments are equally real. The laws of physics, the equations that we use, don't say that there's anything special about now in any way. In fact, all the information in now is implicit in all the other moments in the history of the universe. So I don't think it's anything that physicists ever talk about, and sometimes you worry that it's just a fake question. But the physics itself is pretty clear.
Yeah, because I recently addressed William Lane Craig in one of my videos. He's trying to basically bring down special relativity with hilarious results. I think it's all about the Kalam cosmological argument. He needs the A theory to be the correct one, because that means there can be absolute time or something like that. Do you have any idea what he's trying to talk about? Or is it just the ramblings of an idiot?
Yeah, I don't know what he's talking about in that particular argument, but Craig is exactly doing it wrong in terms of how to learn about the universe, because and some physicists do it wrong too, in the sense that you first decide on a bedrock principle, and then you go make the universe follow that principle. But that's not how good science is done. You should be open-minded about what the universe does, and then go out and ask, go out and look, which way is it actually doing it? So these arguments that Craig has that says that comes into existence at a moment of time must have a cause, something like that. The answer to them is just no. Maybe they don't. Let's go out and look. Yeah. Let's believe what the universe actually does. Let's not just think that we can reason our way into discovery.
Yeah, and that's a brilliant response, I think, to the cosmological argument. That just premise one: everything that begins to exist has a cause for its existence. Okay, really, prove it.
Yeah. How do you know?
We haven't seen everything come into existence. We might predict that it does, but if we're going to talk about logic, then we need proof, not just, that it would be proof by inductive reasoning.
That's right. I don't like to use the word proof, because I don't think that science works by proof, but we make hypotheses and then we test them. We don't make demands. That's not how science works.
Correct.
Okay, Marty, anything else or chat room questions?
No, we are running out of time now, so I guess I'm going to ask while I still have a chance. You mentioned books you could recommend.
Yes.
Especially when it comes to general relativity, because that is something that I'm really interested in. And I know that the best answer is probably, dude, go back to school, but that's just not a possibility where I am in life right now. So
sure.
I'm trying to learn on my own. I don't plan on becoming a physicist. I'm a physics teacher, and that's good enough for me. But are there any books on a fairly technical level? I want to learn the math.
Yeah.
What would you recommend?
So there is. What I was joking about was I've written a textbook in general relativity.
Yeah,
Space-Time.
That sounds familiar.
Right, and it is pretty technical, but it tries not. It doesn't assume that you have a lot of knowledge. It just assumes you have a lot of courage. It assumes that you're willing to pick things up quickly and accept them and move with them, rather than sort of spending a lot of time making sure that you understand all the basics. So you could take a look at it. In fact, on my website there is a lecture notes version, which is only about half the book, but it is free and it's the same spirit.
Cool.
So you can take a look at that. And the other one is there's a book by Bernard Schutz, Schutz.
Yeah.
He's written a couple of books about gravity, but one of them is in this sort of medium level where there's a little bit of math, but not too much. And that would be the other one. I'm not too familiar with it, but that sounds like maybe what would be useful to you, so you could take a look.
Yeah, because I have sat through the lecture series that Leonard Susskind put up on YouTube, which is supposed to be I don't know if you're familiar with it, but I thought that was really great. And I learned a lot from it. That was sort of, I could follow the math sort of. I couldn't repeat it, but it was good enough for me. But I want more, you know.
Good.
So
Good.
yeah.
More out there.
I want more. You know?
Hello, John.
More out there.
John, can you mute your stream, please?
You guys are anyone again?
Yeah. Hello, John. John, can you hear us?
Yes, I can hear you.
All right. So ask a question.
John, can you hear us? Yes. Yes, I can hear you. All right. So
John, just on your screen, can you mute the Von live stream, please? Because that's where the echo's coming from. If you just close your browser, that'll be fine. Yeah, I think that's it.
Sure.
No, it's not. So, John, are you hearing us okay now?
Sorry about that, guys.
That's no problem at all. We have 8 minutes left, so you've just got in for a question. So, ask your question for Sean.
Hey, Sean, thanks for doing this. Really appreciate it. My question dealt with the cosmic background radiation, the new maps for apparently showing some massive object where it's kind of curious that there would be a massive object due to the, at least from what I understand about the current inflationary models. Have you looked at that research? And I was wondering what your thoughts were about it.
Yeah, there's you know, to the 99% level, the thing about the most recent results from the Planck satellite that made the map of the microwave background is everything fits great. That's, you know, it's really amazing how precisely the cosmologist's theory of the universe fits with what data we're actually getting. So, but of course, you instantly go towards the tiny little ways in which it doesn't fit perfectly. And one such way is that on very large scales, it looks like the fluctuations from place to place are bigger in one hemisphere than in the other hemisphere. There's more deviation in temperature from point to point on the sky. And there's maybe even one spot where it's a lot colder than it should be. Not a lot colder, a little bit colder than it should be. So the question is, are these just lucky accidents? Is it just an unusual thing that there's only one universe we can observe, and sometimes when you flip a coin, you will get heads 8 times in a row? Or is it really the sign of something going on in the early universe? And it's just very, very hard to tell right now. I can tell you that trying to come up with theoretical explanations of these phenomena is very difficult. I tried. You can try to write down a model or a theory. The good thing about science is you can write down a model, then you can make a prediction using that model, and I come up with a theory that fits this piece of data, and you get another piece of data. So it's not a simple explanation if it's actually something significant. It's something subtle and complicated. So there's still a very good chance it's just an accident or it will go away. But right now I wouldn't want to draw too strong conclusions about it. I would just want to keep it in mind as something to pay attention to.
Cool. Thanks a lot. And Marty, love your videos, man.
Thank you.
All right. Thank you very much, John. Okay, Kitch, there was a chat room question which you were going to field. You're muted, Kitch.
Oh, brain fart.
All right.
Okay, one question from the chat is, does Sean have any tips for young students who are looking to become physicists?
I think there's no secrets to becoming a physicist. In terms of the basic training, go to college, go to graduate school, take all the courses you can in physics, some of the courses you can in math or other kinds of science, and don't wait for the courses. Read ahead. In this day and age, there's just no excuse not to get articles from the web or get textbooks and do it yourself. I remember when I was a student, I just complained that there weren't this course or that course, but that was a dumb complaint, because there's no reason why I can't teach these things to myself. And then, the crucial point comes, the point where it's not obvious what to do, comes when you enter grad school. And then you're not just taking courses and doing problem sets anymore, but you're starting to do research. And you get to the point where there's no answers in the back of the book anymore. And the trick there is to really take the initiative, to really start doing work that is interesting and interesting to other people as well as to you, and yet that hasn't been done yet and that you can do. And this is really hard, to try to find research that hasn't been done yet that you can do and is interesting. I mean, if it's that interesting, why wasn't it done before already? So there's no secrets there. I mean, there's no trick. It's just, do your best at it. Don't wait for it to come to you, and have a good time. Enjoy it, because there's no reason to do it if you're not having a good time.
Okay, Marty, last question, because there's 4 minutes left.
No, I actually think I have exhausted my supply of questions. I'm really satisfied with the answers I got. So thanks a lot, Sean.
Okay. Well, we've got 3 minutes. We've got 3 minutes left, and usually we allow the guests to get in their soapbox and promote anything. So here you go. You can anything you want to promote or.
Well, so I already mentioned the textbook. I've written a book about the Higgs boson, and my previous book, From Eternity to Here, was about the arrow of time. And I also have a blog at my website, which is preposterousuniverse.com. Recently, I launched a little bit of a controversy, even though I thought I was coming in at the end, but I wrote about why I won't take money from the Templeton Foundation, which is this organization that has a tremendous amount of money and likes to sort of reconcile science and religion with each other. So nobody agrees with me because I will not take money from Templeton, but I will work with other people who take money from them. So I'm not an absolutist on either side. So nobody agrees with me, and it was republished as Slate and got 3,000 comments. So apparently this is an interesting topic to a lot of people. But anyone's willing to come to the blog and join in. I mean, everyone's welcome.
All right. And do you have any books in the pipeline at the moment, Sean?
Oh, you're fading away.
Oh, sorry. I was just asking, do you have any other books in the pipeline at the moment that you may be working on?
I do not have more books in the pipeline. I'm just writing science articles right now. This is back to being a researcher after too much time writing books, so it feels good.
And I suppose we do have more time left. So what's the day-to-day work of a theoretical physicist then? It's I suppose it's maybe a silly question, but
it's more or less a guess. My kind of physics is simpler, so I don't even use computers that much. It's not like I'm not collecting data. I'm not doing simulations. Me and my students and my collaborators, we're standing in front of a blackboard and we're writing down equations and we're saying, well, maybe it's like this, no, maybe it's like that. Well, let's go off and do a calculation. And you do calculations, and you write papers, and it's very, very much a community. It's a collaboration in the wide sense, right? There's a very small number of people in the world who do this kind of theoretical physics. So reading other people's papers, going to seminars, talking to people, collaborating widely, and gradually, bit by bit, we understand a little bit more about the universe every day.
Okay. So we are up to the last minute, so we'll just wrap up there. Everyone, a big thumbs up in the chat room for Sean for taking the time out to appear. It has been fantastic. It's been really interesting. And thank you to my co-hosts, Kitch. Thanks and welcome back.
Cheers, and glad to be back.
And Marty, thanks for coming along.
My pleasure.
And we'll say thank you to Womble. She's not around at the moment, but thanks to her for helping out. And we are back next week, and it's the live ponage of Mr. Ian Juby. Mortimer, quickly, who and what is Ian Juby?
What?
Who is Ian Juby? Quickly tell info.
He's a creationist who looks like a walrus.
All right, there you go. So you got that to look forward to. Same time next week. Thank you everyone for tuning in, and have a good evening, afternoon or morning, wherever you are. Thank you very much. Goodbye.
Thanks, guys.